Hello, hello, hello. Eh, hello, hello.
Didn't ask me. Okay, here we go. Oh, I'm sorry. I didn't really connect the audio. Somehow this is just the WebEx recently changed.
Yes,
You can hear me now, right?
yes.
Okay, that's good. It's actually raining. It's good you stay home. Let's start with the exercise still. I think should be pretty easy. It's just go forward with it, okay? I will share my desktop with you. See it? You see it? You see it, right? Okay, start from the limit. The limit thing actually pretty easy. We just right?
Yeah.
For that one, so basically you need to find the limit for the the first line. So what do you have?
6. 6.
X equal 6. You sure? 6?
Yeah.
Let's see together, okay? I think it's a bit different. Okay. I was playing with it. That's with 7. It is 2x plus 5 minus so that thing just to get plus square root of x plus 7. Then goes x minus 2. Oh, okay. So you cancel out that one and that one. You got, oops, Gosh. Let's go with the right, whatever. So you have x equal 2. When x equal 2, you get square root of 9. Square root of 9. Oh, 1. So 1 over 6. Did you say 1 over 6? Huh?
I said 6.
Oh, okay. Okay. So 1 over 6. Right?
Mm-hmm.
Oh, okay. When k equal 1 over 6, then it's continuous. That one is, oh, that's straightforward. Okay, this is a kind of faking. So what do you have this one?
0.
0, did I copy it wrong? It's, let me see. It goes to x or goes to infinity or goes to 0? It goes to infinity? Wait a second. It goes to infinity. Actually, I will think, so that is a 0, that's right. How about, another one? How about that one? Why cannot? It's too crazy. Okay. How about limit x go to 0 sine react over 6x? Actually, I should do already using whiteboard. Whiteboard you can write, but you don't have the pen to write. So anyway, just say it.
Half. 1/2.
1/2. Yeah, that's it. 1/2. We are say x equals -2. What do you have this?
Oh.
0?
12.
12, yes. What about this?
0.
0?
Mm-hmm.
0? No. Actually, it can be factorized. The bottom can be factorized. Oh.
Oh, scroll. Okay.
What is it?
1/8.
1 over 8. Okay. Going as the Lant. Find the equation.
X minus 2. Y equals 3.
I'm sorry, say it again.
Y equals -3.
X minus 3?
Mm-hmm.
Okay. Good. That one actually, anyway, it's a parenthesis between that. Let's see. Oh, it's parenthesis between them. Should have it. I didn't. Anyway, so what is this?
I don't know. But I guess here.
Let's get together. So, anyway, so, infinity. What is that? Square root. Plus 5x minus. So this symmetric has one exercise. So you just put there as 1 over. Why is it coming? Oh, because here is 230. All right, so you put square root of 4x squared plus 5x plus square root of 4x squared plus x. Then the numerator become 4x squared plus 5x minus 4x squared minus x. Right? So it's going to become only 4x in the numerator. Then become this thing still copy. Then we divide x. Divide x in both the numerator and the denominator. You have that. Then you have 4 still in there. Divide x, then you have 4, then plus 5 over x plus square root 4 plus 1 over x. So as when x goes to the infinity, this one disappears, goes to 0. This one disappears, goes to 0, right? So the final value goes to 4 over 4.
Okay.
Is 1. So let's try and give you another one. You just demo to like a 2x squared plus 1 and minus square root of 2x squared. Let's get to the next page. Okay, let's do in the one exercise. Square root of 2x squared plus 2x minus square root of minus x. Okay, so still x goes to infinity.
Okay.
Definitely this means parentheses.
Three over 2 square root 2.
Okay, good. Let's move to the basically the what is that mean really? A little bit explain. Okay, here is the infinity. Okay, here is also infinity. Those two infinity not different too much, only a little bit. Actually, it's a constant. So when x goes to infinity, those two infinity very, very close. That's it. Okay. But if you have like a square root of 2x plus 2x, then minus square root of x, when it goes to infinity, let's go to the infinity because this one is faster. Okay. This one is slow than that one. Okay. That one. I think I copied wrong. Is that right? Huh?
I think it's x goes to 0.
X goes to 0, right? 135 x goes to 0. So the value is 0. Okay. This one we did already. This one we did already, essentially, right? Find the asymptote of that function.
X equals 1, y equals x.
Okay. X equal 1, x equal minus 1. Y equal x, right? Okay. This is yeah, the button, the answer. Sorry, you saying the answer already?
2.
0?
2.
Huh. You saying 0?
2.
Oh, 2. Oh, 2. I'm sorry, that's 2. Okay. The same stimulus. Yeah, this is almost exactly the same thing. So the answer is.
So yeah, 3 over square root 3.
Yeah. Huh? Say it again. One more time.
3 over square root 3.
Oh, why do you need to go over there? You're saying 3 over square root 3? That's square root 3. Right?
Let me see.
I'm not sure why you get that though. Because you have square root 3x square 17x, then you divide it by x, then you have square root of 3 plus 17 over x. So still same thing. This one goes to 0. Okay. Limit actually is very easy in many sense, right? Okay, now that's good. Let's move to the complex number. This topic, as actually will extend the knowledge to really the number, then it's going to be the next chapter 9. So real number. Let's go to the complex number. This probably there are some typo. Okay, I actually was just find out. So I squared is -1, right? So we also saying square root of -1. Just in that one, treat as I. That's all. So you have a square root of -4. It's going to be 2i. Okay. Then let me go. Okay. So those just a complex number, like 3 plus 2i, 4 minus I, -1 plus 2i, just a complex number. So you already know this. It should be pretty good, right? And the addition, subtraction, multiplication, then division. Let's just try to see if you forgot or not. Let's try to see what is 1 plus I squared, for example, equals to
1 plus 2i minus 1. So 2i.
2i. Good. Still remember. So for the complex number, we also define the real part is the real number, the first part. So the imaginary part is the coefficient of the I. It's also a real number. The imaginary part and real part are all real. So it's not imaginary. So also we define the conjugate. Remember the conjugate?
Mm-hmm.
Yeah, you also learned something like, actually, you know, the previously like we did like this. So yeah, anyway, just move. Okay, so the next is called complex plane. This is really so what that means is you can plug every number, every complex number, you can plot it in the plane. So that plane essentially is the Cartesian plane, same plane, but we just give every point just different, like 3 plus 2i is over there, like 4 plus 3i is over there. You see it? We have, for example, if we have actually if we make a complex plane like this, so like this, if we say, what's going on here? Oh, really? Interesting. Oh, I cannot read like this. Okay, right. Okay. Now I can write it. So, like, say if I had saying here's 1, 2, 3, 4. There's 4. What? It's like okay. So I don't worry. I don't want to like using this. Just using the manual. You make a complex plane like this. So 1 is here, 2 is here, 3 is here, 4 is here. And here is I, okay? So here is 2i. So here is 3i. So for example, this point is going to be 3 plus 3i.
Mm-hmm.
So what is, for example, what is here is going to be negative I, negative 2i. Here is going to be negative 1 still, negative 2 still. That's all. So where is like minus 3i? So it's going to be here. It's going to be here. This will be the here.
Mm-hmm.
So essentially it's the same the Cartesian plane. So we can also say in the Cartesian plane, this is the point corresponding to the xy coordinate 3, 3, right?
Mm-hmm.
So here is like minus 3, minus 3. So here is, this point is going to be 4, 3. This is called this the rectangle Are you busy? And then rectangle coordinate. So is your phone or your home phone? Okay, need to answer.
Mm-hmm.
Okay. So we remember we also learned something called polar coordinate.
Mm-hmm.
For example, polar coordinate, this one has the polar coordinate is going to be 3 square over 2. Then actually theta is 45 degrees, so it will be pi over 4. right?
Mm-hmm.
So that point 4, 3 is going to have the polar coordinate 5. Let me write it here. 5, the arctan 3 or 4. Okay, so the polar coordinate. Okay, let's move on. So you are that's all just essentially just a point in the plane. You just see it differently. So you see it as complex number, then that's fine. You see it as the rectangular coordinate, that's okay, XY coordinate. So you see it as the polar coordinate, that's okay too. When we learn the plane geometry, we don't see anything in there. We just see it's a point, okay? Because we don't really care about exactly where it is, just care about the relative to something else, right?
Mm-hmm.
Okay. That's it. So every complex number is corresponding to a point in the things called complex plane. You just call it complex plane. It's just a plane anyway. So I already said complex plane is identical to the Cartesian plane. So polar coordinate is I used in this example already. So 4 plus 3i as the rectangular coordinate for 3, then has the polar coordinate 5 arctan 3 over 4. So on the other hand, you can convert back. If you have the rectangular coordinate for 3, then we corresponding to the complex number 4 plus 3i. That's good.
Mm-hmm.
So polar coordinate 5, then arctan 3 over 4, we corresponding to the complex number for 3i, that's definitely. So in general, you can say the rectangular coordinate xy corresponding to the complex number ix plus iy. The polar coordinate r theta, that is a little bit interesting, is r cosine theta plus I r sine theta. So that's actually you need to pay attention a little bit with it. Let's just make a different color. So if here like 3, 3, then the theta actually is pi over 4. So it's a cosine, remember it's cosine theta, then plus I sine theta. So this in here the sine is positive, cosine is positive, right?
Mm-hmm.
So here the theta, for example, this point is -3 plus 3i. So when you come to the polar coordinate, it's going to be 3 square root 2, then 3 pi. So this is exactly right because here sine still is positive, cosine is negative. So the x is negative. See? So here at the -3, so -3. I'm sorry. Here is the. Oh, here is the right. Yeah. No, this one corresponds to that one. So here actually is going to be 3 square root 2, then 5 pi. So you have the things here going to be 3 minus 3, or you think 3 minus 3i, whatever. Then you're going to have 3 square root 2 then here is 7 pi over 4. So here is exactly right because sine is positive, sine xy. Sine is negative, actually cosine. So sine is negative, cosine is positive, right? Okay, it's all easy. Okay, now an example. So, oh, we already have the answer. So find the polar representation of I, which is 1 and pi over 2. So what is the polar representation of negative I?
1 negative pi over 2.
1 what? Oh, what do you say?
1 minus pi over 2. Or like 3 pi over 2.
Yeah, actually I think that's okay too. But usually we say positive theta, usually. Actually negative also makes sense. But we say negative I is going to be 1 over 2. I think it also works. So 1 minus pi over 2. But usually we don't say that. That's just the way it is. It really works too. So for a complex z, under the polar coordinate has coordinate r6. Number r has the name, okay, called modulus of z, also called the absolute value. This really is the distance to the origin. The same as the real number. Yeah, usually called the modulus just for some reason. The angle, actually I didn't write here, it's called argument. The angle theta is called argument. Do I have it? No, I don't have it. Okay, so argument. That one called modulus, one called argument, so 2 words. So you can say 4 plus 3i has the modulus 5. 1 plus I has the modulus 2, square root of 2. Actually, we have a little bit of exercise. Maybe we should do a little bit of exercise with it. It's hard for you to do it because I cannot see your join. That would be a problem. Okay, let's move to. Yeah, you just move to the next thing anyway. So the arithmetic you already know, the multiplication, right? So 4 plus 3i and 1 plus I, the multiple together is 1 plus 7i. So 1 plus 7i, the modulus is 1 plus 49 and square root, which is 5 square root of 2. So you can see actually the modular will have this kind of so-called theorem. The modular z times the modular w is the same as the modular of zw. Or if you like, you can send the absolute value. Absolute value of zw is equal to the absolute value of z times the absolute value of w, right? Okay, the proof is in the book. It's on page 90. But I can go with you a little bit. Okay. Annotation. How? How you can do anything? I'm never using the whiteboard. Can't you? You can try. They're working? I think allowed. Still ask me. Okay. Is that working? I cannot really see anything. Actually.
This one?
Huh?
You see this? You see this?
Oh, I see it. Okay. Oh, it's disappeared. Yeah, I can see it. You can do it again?
Okay.
Huh. Where? Oh, I can see it. Okay, it's pretty good. Pretty good. It's only like a join on my screen. That's good. So you use the mouse, right? Yeah, mouse is pretty hard to join. Very good thing. Yeah. That's the thing. That didn't work. I don't which button did you click to make it work?
The thing which is like asking to annotate, asking to.
Oh.
Asking to
you can type too?
Yeah.
Oh, that's cool. So same way same time you can still see my screen. You see you're typing there.
Yeah. Your screen is underneath the typing.
Oh. Okay. Okay, we'll learn. Oh, okay, everywhere. Okay, we'll learn how to use that thing. So I should be able to do that too, right? I don't know. I'm never using that kind of.
Oh yeah, I don't know there too. Wait, see now.
All right.
All this stuff.
Oh yeah. Okay.
I don't know how to.
Actually, yeah, in the future, maybe everybody will go buying this kind of pen. You never know, because the pen can really do a lot. Oops. Oh, it's not allowing me to write anymore. As long as that thing, it goes to you, I cannot write anymore. I have to stop the annotation. Then probably then I can write it. Oh, you and what that mean? Let me see. Oh, where is it? Oh, can you still write?
No.
You cannot anymore.
Yeah.
Now you can. Oh, okay. I see. Okay. All right. Anyway, so the proof is pretty straightforward. So you just have maybe I have. We just have saying z equal a plus bi, w equal c plus di. Then you find out. So essentially, you need to prove a squared plus b squared times c squared plus d squared equals to AC minus BD squared plus AD plus BC squared. So the key is the cross term is cancelled out. See, everyone has 4 terms. So you have a squared, c squared plus a squared, d squared plus b squared, c squared plus b squared, d squared. The same thing here. So that's it, right? Okay, so this is easy. So this should be natural. The next theorem is very, very important, okay, called triangle inequality. Why it's called triangle? We are going to learn this one a little bit. Actually, yeah, we can see it. Let's see here. So this one is called Z plus W. So always less than Z. Let me explain a little bit with it. So if we have here, let's say Z equal 1 plus I, W let's say 1 plus 2I. How about it? So Z is basically here, right? So W is here, right? So you can think here is Z, here is W, right? So Z plus W is going to be MG2 plus 3I, going to be here. So what that point is really is to make the
Oh yeah, it's like vector.
parallelogram, okay? So that's really is saying, so this here is really like Z plus W. So that triangle so has the length of Z. This is the length of Z plus W. Sorry, this is Z. This is W. So this is the I didn't really show you a very good picture. So here is the Z plus W. So this one is called triangle inequality because here you really have it a triangle. Okay, so the triangle inequality. The proof actually is very easy. So you analyze it if you have Z equal A plus BI, W equal C plus DI. So you just figure out what really need to prove. So you want to prove A plus C square plus B plus D square is less than the square root actually, so it's going to be square again. Square of Z, which is A square plus B square plus square root of C square plus D square. Right? So if you expand it, it's going to be A square plus 2AC plus C square plus B square plus 2BD. We want to prove we don't know yet. Okay? A square plus B square plus C square plus D square. Then you have plus again 2 square root of A square plus B square square root of C square plus D square. Right? So you don't want this, don't want this. Hey, where is I missing one? C square, D square, missing D square. Okay, so missing. So really, you want to prove AC plus BD less than right. So you still don't know yet. Expand it again, you get So you cancel out a squared, b c squared. You get 2a, b, c, d. So let's say want to prove this is going to be a squared, d squared plus b squared, c squared. So this is you need to prove, right? But this one is the same as 0 less than AD minus BC squared. This is always true. So this is always true.
Mm-hmm.
Yeah, somehow this can get responses slowly. Okay. Anyway, this is always true. So this is also always true. So get this one is always true. Okay. Get it? So the most important thing is when the equality holds. Equality holds, you find only if AD equals to BC, right?
Mm-hmm.
So let's see. Oops. So if find only if A over C equals B over D. Or if you think this is a number K, for example, it's a real number. So if find only if Z equals to K times W, right?
Mm-hmm.
So equality holds. This is called that's a name called linear dependent. So actually Z and W, if you join in the plane, it's going to be the same thing as ZW. So Z equals to, for example, 2W. What that means? If you say here is W, then here's going to be 2Z. All right, going to do 2Z, something like that.
Oh, yeah. So the triangle, the triangle.
Okay. Yeah. So you're saying, so that's what really means. So Z equals to 3W is going to be 3W. So, okay. So if find out, because in this way, then when they add up, then coefficient just add up nicely. Like say 1 plus 2i, then 2 plus 4i, right?
Mm-hmm.
So this one, the absolute value equals square root of 5. This one, the absolute value equals square root of 5. So add up together 3 plus 6i, then add together is 3 square root of 5. So this one holds because 2 plus 4i equals twice of 1 plus 4i. Okay? So this is the if and the only if. This is very, very important. Okay? If and the only if. So let's see. This triangle inequality is very, very important. So x size 9-8 compared to 91.
Mm-hmm.
Then what is the equality condition of the triangle inequality when W and Z are written in a polar form? Okay, that's really interesting. Okay.
So that just their angle is the same. So.
Yeah, theta are the same exactly. So that would be either saying R1 theta and R2 theta. Same thing. That to be same thing. Okay. The next exercise called 9-9. So I would say it's really nothing. Because Z is same as inequality, but actually you can see that differently. The geometry is really different. You can say this is less than Z plus W. Okay, can say it that way. But the geometry can be really explained a little bit different. Okay, that's okay. Next thing. Let's go back to the next thing. So this example explains W plus Z, which is square root of 5, less than 3. And the absolute value is W is 2, absolute value of Z is 1, so add up together is 3. So this explains why it's working. Just an example, really nothing. This is example, is the exact example I just gave to you, right? The proof, actually we just did the proof. Have to do the exercise. We did the exercise. Okay, that's all good. So the next thing is about the multiplication. It's very, very important in the polar coordinate system. So saying W has the polar coordinate system with R, alpha. Then Z has the polar coordinate system has this, S, then beta. Clear, right? Then the W, you can write actually W as, don't need that anyway. Something funny. Anyway, so write W as R cosine theta plus I sine theta. Then we have Z equal R, S, then cosine theta. Oh, cool, no. No. I think I call cosine beta. Also, I call this one alpha. Call this one alpha. Then W times Z is going to the slide. So RS, okay, the cosine alpha plus beta. I didn't really explain that thing. So it's saying you're just doing the distribution. So RS cosine alpha cosine beta. So the imaginary part gets minus sine alpha sine beta. So the I part is plus I times, which is cosine alpha sine beta plus sine alpha cosine beta. Let's say, right? The thing is, this is the cosine alpha plus beta. This is sine alpha plus beta. Okay.
Mm-hmm.
So this is very nice. Yeah. Especially if say you have the W time W itself. Right?
Mm-hmm.
Oh, sorry. I'm still missing. Okay. Now, example 9-2. I think we have it here. For the number, whatever you call it, cosine pi over 3 plus I sine pi over 3. This slide of here is exactly as the book. So if giving any number r cosine theta plus, actually misspelled here. I missed the I there. Missed the I there. Let me change it. Let me change it. My gosh, I don't know what it is. Huh. Missing the I. There you go. All right. Unfortunately, this thing doesn't work very well. I have to restart it. There you go. Okay. The I back. Okay. That's it. The good thing. Oh, I have to move a little bit. There. It is. So, the multiply G multiplied by G is the same as rotate the Z with the angle pi over 3. Yeah, we talked about it a little bit, right? Just to remember the transformation, we only did one. Actually, I emphasize saying that one was very important. The coordinate change thing. Anyway, so for this G, you can have G squared equal that, G cubic equal that. Actually, G to the 6 is going to be 1. G to the 3 is minus 1. G to the 6 is 1. Okay. So xi is 9-10, 9-11. And let's take a break for like a couple of minutes. I'll be back in a couple of minutes, okay? Okay, I'm back. Okay, 9-10. What is it?
90 degrees.
90 degrees exactly. So 9-11. Join blah blah. Set yourself. Go set from product. That's a little bit hard. Little bit hard to really convince yourself. But oh, okay. Let's move to the next thing. Okay, this in general. That's very, very important. I'm sorry again. So Mr. I again, second term. Okay. Good. Okay. I because actually this is probably the only chapter I didn't really have the slide with it. So that's why. The next several chapter I all have a slide with it. As new technology still has some problem with it. Anyway, it's much better than before. You know, before it's very hard, and remotely I want to show you kind of mathematical formula slightly. It's pretty hard. Oh, didn't change. I think it changed. One didn't change. No, anyway. Also true for the negative power. This is very interesting. How do you say it? Just multiply both of them. Just leave there. Just leave there. It's actually hard to leave there. I still have one. Oh, I think I just changed the wrong place. Oh, here there's one. So many places wrong. There we go. So how do you approve the second thing? Remember last time we replayed something with from like a functional equation thing. You play from natural number, then to the negative number, then to fraction, then to real number, those kind of trick, remember? Same trick applying here. So we have the positive integer, then we can do negative integer. How do you do the negative integers like this? So you say R cosine theta plus I sine theta. The negative end, I don't know what it is. I just multiply it. So R cosine theta plus R sine theta. I. Then to the plus end. Then this is the 1. Okay? So this one is known, right? So we got R cosine theta plus I sine theta. Negative 1 going to be R to the negative 1, then cosine theta plus I sine theta. Actually, we already know n is over there now. Already know it's n theta plus I sine n theta. But has the negative 1 there. Right? Because you just divide that one. Got it? But that one, fortunately, this one multiple that one, so is also 1. So you can cosine negative n z plus I sine a negative n z. So time cosine n z plus I sine n z equals to 1. So you get the negative can goes into there. So forgot about that. Something wrong with this computer. If you forgot about this, then this one you continue with. It's going to be okay. Right? Next thing actually is about fraction. Fraction is a hard thing. Okay, fraction is fraction. Then you can have 1/2 can be that way because you have you have cosine plus I sine 2 to the 2. Actually, we only care about we don't really care about that. We only care about 1 now. Actually, I'm okay. Let's think that we only care about that kind of thing. So is equals to cosine theta plus I sine theta, right? So that is, which means the cosine theta. Which means cosine theta over 2 plus I sine theta over 2 should be equals to 1/2, right? But the problem is you see the cosine. Oops. Plus pi, then plus sine is essentially just rotate the pi. This is just a negative thing. So that thing, if you square it again, you will see it's also equals to cosine theta plus I sine theta. Because the sine 2 pi is nothing in there, right? So which means the cosine theta 2 plus pi plus I sine 2 plus pi can also be equals to cosine theta plus I sine theta over 2. Actually, this is true for general. Like we say, like what is the root of, like saying essentially it's just saying solve the equation of how many solutions it has. It has 2 solutions. So one solution is this. So another solution is this. We can also write this one as cosine theta over 2 plus I sine theta over 2, then times cosine pi plus I sine pi according to our, right? So this is only -1 by the way. So just multiple -1. This is definitely true. So if something square that equals to that, then multiply the -1 still get the same thing. Let's move on to what do we have here. Because sine and cosine have period 2 pi, you can have that one. So the fraction power, this is very, very different from whatever you learned before. This is totally new. So the fraction power is not unique. So essentially, I already told you that one. So essentially, this one just the square root of z and the minus square root of z. Okay. Because before you like saying when you learn saying in the 6th grade or 7th grade or whatever, the teacher told you like square root of 2 or square root of 4, whatever, square root of 2. Then you can tell, okay, so what is the root? Which number has square as 2? Then you can have let's say square of 4. So which number has square as 4? You can say 2, negative 2. But then tell you saying 2 is the arithmetic root. So then actually if you learn square root of 4, then we always mean square arithmetic root. But it's really saying because the square root of 4 is come back to a real number, you can tell saying which is positive, which is negative, right? Then if you come back like a square root of 1 plus I, then it's hard to tell which root is real, which is positive, which is negative. Both could not be negative, could not be positive. It doesn't make any sense. So I cannot compare I with anything. Okay, there is no comparison between. So there are 2 roots for it. Okay, so let's give you another example. We already learned that when omega equals to -1 minus square root of -3 equals cosine 2 pi 3 plus I. Then we're going to have cosine theta plus I sine theta 1/3 going to be, I'm missing the I again, over here. So it's going to be like this. It's going to be 1 root. Also, you're going to be another root. Then going to be another root. So it has 3 roots with it because the omega to the 3 is 1. So this is always true for the n's. So let's talk. So essentially, it's only like saying one the root of root of unity only saying nth root of unity only matter. You know, it's only saying the previous example you're saying essentially you're saying z then square root, you're going to have square root of z, then the minus square root of z. So the minus 1 is what? Minus 1 is the number with -1 square equal to 1. Is the so if go to the cubic, you have z, whatever you take 1. Then you have omega z. Then you have omega square z. Okay. That's it. So when going to the fourth, you're going to have z, then whatever that thing. For example, we can give you an example. Sorry. Then going to be I, then -1, then I. For example, x to the 4 equal to the 2. How many? Maybe 2 is better. Maybe to 16. how many solutions we have are going to have 2. We're going to have 2 and 2i minus 2 minus 2i. Those will be the outer root. Okay. So see, now we're talking about the nth root of unity. Then we have the following numbers are nth root of unity. Cosine 2pi over n plus I, cosine, then the next one, then next one. Then totally you have n of them. The last one is 1, okay? You see it? The last one is cosine 2pi plus I, sine 2pi, so it's 1. Right? So, for example, you can see how many solutions of the xn equal to 2 have. They have all those solutions. How many solutions like xn equals to the cosine pi over 4 plus I sine pi? So I'm missing a lot of I there. Oh. There you go. Every here is I. Okay. Okay. What? Go back again. There we go. There we go again. Okay, here we go. So you have that equation. So that's all. So essentially, it's only the root of unity matter. So solving those kind. Okay, the last one is not. Huh? Oh, okay, that's right. So is that right? Yes, that's right. The cosine pi over 4n plus I sine pi over 4n is 1 root. You only care about 1. Then the rest only generated by the root of unity. Is it already confused?
No.
Okay, that's good. So actually, that's thing we talked about the last time. Then this for real number y. Then you have the e to the I y is going to be cosine y plus I sine y. So this is not only saying is saying formally it's a real equal. Where is the? Why can I say it? Huh? Oh, I see. It's slow. It's still doing. Still trying to load it. Huh. Okay, here we go. Gosh, what happened? Anyway, so the key reason is last time when we learned that thing, we didn't do one more exercise. So E is 1 plus 1 over n, or n, when limit when n goes to infinity. So you can easily see e to the whatever z is going to be limit 1 plus z over n. This is the expansion. I didn't really talk to you too much about that then, so it's going to be 1 plus z plus when n goes to infinity. So the e to the iy as the expansion with 1 minus 1 plus iy, then plus, let's say these 3 factorial, 4 factorial. So when you have square, then you got to have minus. Minus y squared over 2 factorial. Actually, it's going to be minus again y cubic, then 3 factorial. And get 4, then get 1 again, get y to the 4, then 4 factorial. The 5 get I to y 5, then 5 factorial. Then get 6, 7 again is going to be negative y to the 6 factorial minus 7 factorial I y to the 7, blah blah blah. So keep going. One thing actually, I just want you to accept it right now. So sine y going to be y minus 3 factorial y cubic plus 5 factorial y to the 5 minus 7 factorial y to the 7. And keep going. This is true for every number y actually. So even can prove for the complex number. I need a little bit calculus ready to prove it. So cosine y as if you learn calculus in next year you're going to have this. It's not that much. So limit, then derivative, then Taylor expansion. Pretty much just 3 more class lesson you're going to have it. If you learn calculus. So that e cosine y is going to 1 minus y factorial 2. Oh, sorry. Y square over 2. Then plus 4 factorial over y to the 4, then minus 6 factorial y to the 6. So pretty much you see that's you see that thing that basically cosine, right? So this equals to cosine y. So you have y here. Then you have 3 factorial here. So basically plus I sine y. So e to the iy equal to cosine I plus I sine y. So we don't want to prove it. I just want to tell you the reason is because there are actually other proofs for it, and some pretty good proof. Need a little calculus to work on that thing. That's about it. So, but this is a super important formula. Okay, very, very handy. Let's see a little bit with it. So, for example, e to the pi I of 2, which is I, right? According to that, it's going to be cosine pi over 2, which is 0, plus I times 1, which is I. Right?
Mm-hmm.
Do you get it?
Mm-hmm.
So e to the pi I is going to be minus 1. E to the 2 pi I is going to be 1.
Mm-hmm.
So in this way, the root of unity we can write as e to the 2 pi I over n, e to the 4 pi I over n. I'm not sure you still remember the root of unity. See here the root of unity. So the first one is e to the 2 pi I over n. The second one is e to the 4 pi I over n. And last one, yes, e to the 2 pi I. So this is 1. So the root, yeah, the last one is the e to the 2 pi I n cancelled. Okay. Next, are you good with it?
Mm-hmm.
So next thing is there's really nothing about it. Then you define the hyperbolic sine, the cosine. You just need to know about it. It's not only true for the real, it can also be the complex. But usually people think about the real number only. So it's for the complex number also works. You also have another one. I didn't really mention it. Maybe I mentioned it here. It's not in my. So e to the x equals cosine x plus I sine x. So assume x is real. So you take the conjugate, you get e to the ix. E to the minus ix is going to be cosine x minus I sine x. So you solve it, you can cosine x equals to e to the ix plus e to the minus ix divided by 2. And sine x can be equal to cosine x e to the ix minus e to the minus sine x equal to 2. That's not really important at all. So yeah, I don't really see any useless with it at all. I never use it. Okay, so just know it. So you can also define tangent. This thing I also never see the useness, but just the knowledge. Okay, just a function in there. That's all. All the root of unity. That's very interesting. Geometry plotting. So what that means is, let me join a little bit with it. Then we end with okay. So let's start with omega. Sorry, actually it's not. What happened? I think my computer already got. You know that one is also is cosine. So also is e to the Okay, so where is it? Is 60 degree here? That's what it is. Okay. This the omega is here. So omega, oh, I'm sorry, actually 3 to pi is 120 degree. Sorry, it's 120 degree. Here is omega. Here is not. Okay. So omega is 120 degree. Okay. 2 pi over 3 is 120 degree. So the next is omega square is here. So the next one is 1 is here. 1 is omega to the cubic. So those 3 points so this is going to be a regular triangle, right?
Mm-hmm.
Okay. Next one, let's see different one. To the fourth root of unity, we already see it is 1 here, then I here, then it's negative 1 here, then negative I here, right?
Mm-hmm.
Those, sorry, this not showing very well. So it's going to be a square. Okay. So usually for the nth, it's going to be just a nth polygon. For example, 8. And you're going to have another one here, another one here, another one here, another one here. You're going to have, usually yellow is bad. It's hard to see. Let's see. No, it's hard to see. Fraction. Anyway, it's hard to see. So just see the hard one. So it's the octagon, right? For the 8, it's the octagon, 45 degree. Okay, so it's a very very beautiful thing with that kind of thing. So you need to get a little time to really get used to it. So the complex plane. So when we think about the complex plane, usually we think about this way. You think about a lot of number, like especially everything on the circle. You know, it's always e to the something. E to the something because it's always cosine something plus something.
Mm-hmm.
So, you know, when let's see let me doing one more exercise. Okay, by the way, the fraction power. If you look at the book on the page 92, 93, then using like the shorthand notation R6, to represent the what is it called? The polar coordinate system, the polar coordinate. It's could be a little bit confused if you're confused, but using whatever I explained to you, should be no confusion. The fraction power also has a name. Excuse me, called the De Moivre rule, De Moivre theorem, De Moivre rule, whatever it is. So, because this thing really is different from your thinking in general. Thinking in general, something like goes to something is unique, but goes to the fraction power is not unique. That's the whole thing. Also, we have a very interesting example on page 95. I to the I. What is the I to the I? You see it? On page 95.
Are you sure that's page 95?
Yeah, page 95. I to the I. So.
Oh, okay.
So the thing is figure out the value I to the I. Okay, how do you find out the value? Because I itself equals to e to the 2 pi I, right? But it can also equals to e to the 2 pi plus 2 k pi, any k, so okay. Right? So I to the I, this is really contradictory to whatever you learned so far. So I to the I could be e to the 2 pi I, then to the I, which is e to the minus 2 pi of 2. There also could be e to the 2 pi plus 2 pi I, then I, which will be e to the minus 2 pi, e to the minus 2 pi. But it could also be equal to 2 to the 2 pi plus the 4 pi, then I, then it's going to be e to the 4 pi. So this question probably can say it's not really make sense. You can also say it has an infinite dependent value. So why is this? Just because to the i's power, that could be there is a theory behind it that can have infinite many branches, can find something like that. So this is a tricky question, okay? So it could have many value. This basically finished. Whatever it is, divide the third unity. Okay, let's look at exercise 9-21 a little bit. So what n is -1 then nth root of unity? For what n that's -1 lie on the polygon? Join about. Okay.
Mm. 2, 4.
Yeah, for the odd even actually. Right? As long as n is even, then -1 is always the root of the unity. Right? Yeah. So the same answer for the second part of the question. Oh, the next one is very interesting. For the 17th root of unity, how many of them are in the second quadrant? So you need to figure out the argue. It's the exercise. Oh, okay. Now you figure out.
Okay. That should be. Because you can do 3 divided by 17.
Huh? Four. Yeah, let me see. It took, I think it's approximately 4 or 5. Let me see, because 17. Let's count, okay? 17. One. Let's count here. It's hard to count there. So the first one is 17, then 2 pi, right?
Mm-hmm.
So 1 is going to be, so the 3 pi. 17 over 4 pi. Yeah, that should be very easy. Sorry, no. 4 pi. No, there's no one. There's no one. Should be 4 pi, then 6 pi, then 8 pi. I think this one is getting there already. No, not yet. Okay. So you have the 17 over 10 pi is in there, right? Then 17 over 12 pi. Then 17 over 14 pi. Then 17 over 16 pi. Then 17 over 18 pi. So basically those are 4, right?
Mm-hmm.
Next example, 9-13, this one. So omega, we talk about a lot. So you just calculate 1 minus omega plus omega squared. Then 1 plus omega minus omega squared. We can do either way, can do expansion, can do a trick with it, can do like 1 plus omega plus omega squared is 0. Then you can do minus 2 omega. Say minus 2 omega squared. Only 4. Right?
Mm-hmm.
Oh yeah, they're doing the So we have one more exercise, 9-19. We're going to do it at home. So 9-19 exercise, then plus the rest of the problems. Then we'll see you next time.
Okay.
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 Okay. Thanks.
Okay. Bye.
Okay. Bye.